So welcome back. I will make a very short recap about Monday lecture to refresh your memory. And for those of you who are not here, just to have a flavor of what we discussed. So this is the recap. So Zrenitsky in the 90s has the good idea to think to the many-body problem by looking at your physical observable in the basis of the energy of the eigenvectors of the Hamiltonian. So alpha and beta, they label the eigenvector, two eigenvectors of your Hamiltonian, and they are uniquely defined by the energy. So he wrote down this ansatz for the typical strength, amplitude of the matrix element, thinking that they were sort of random numbers. And he suggested that the diagonal one is a function of the energy, but actually better to think to this as a function of the energy density. And the off-diagonal one are more subtle, so their signs are completely random because they depend on the phases of the eigenvectors. And they are extremely small. So they are this is the entropy at energy E, where E is the average energy of the two eigenvectors. So it is an expansive quantity, so it is exponentially small in the size of the system. And on top of this, if you want to have some non-trivial dynamics, and you will see today, you need to encode some information about the frequency. I call it frequency, and you understand it why. And it is the difference between the two energy of the eigenvector involved in this matrix element. And then, as I said, this is the typical amplitude of this matrix element, but the defined details, they vary, and you can, and the sign especially are not fixed. And you can think to them as random numbers, where I only tell you that their average is 0 and their variance is equal to 1. Okay, this was the last part. We arrived here, and I told you that you were not able to make a prediction of this type. Only numerical results are present, but we were inspired by a toy model of ETH, where your Hamiltonian is random, is for instance drawn from a GOE. If you draw an Hamiltonian from a GOE, it's eigenvector, so the matrix of its eigenvector are completely random and uniformly distributed. So there is the Ptolemaic structure, and now I want to look to my observable in this basis, which means I can think to my observable as a diagonal path, which is fixed. It's spectrum. This is deterministic. But then I look at it in the basis of the Hamiltonian, which is a random orthogonal transformation. And if I write the operator like this, I told you that you have correlation between matrix elements. Where you average over O, the orthogonal transformation. And I call this number freq. So the content of ETH, if you like drawings, you can write it with drawings by saying that you draw a circle for the diagonal matrix element. The vertex represents the index, and the edge represents the matrix element. And this is your function A of E. And the other content of ETH is the variance of the diagonal. That you can represent like this. The two vertices are different because it's an off-diagonal matrix element. And this scale is very small. and modulated by the function Fe of omega. Now, this toy model for ETH that I started with is saying that in this toy model, there are other this type of correlation, which are very small because this factor here is very small. So it's very large on the side, but the other side is small. And he's saying that this type of correlations are here. I should have said that the all indices are different. That in the same diagrammatic representation, this means that this is just this. And the goal of this lecture will be to talk about correlation between matrix elements. So to this type of correlations. It's going to be a bit technical, I'm sorry. But I thought that it is an exercise to show you this formula because in the end it's easy. And it also, I saw that there was some interest in random matrices. So maybe you already know this result, but if you don't know, it's better to know it. And then, okay, this is for the toy model. And then you can maybe already imagine how I want to go from the toy model to ETH. And this will be useful to talk about equilibrium dynamics. So it's a very different setup for with respect to what ETH was born to explain thermalization, so non-equilibrium dynamics. Here we just have more easy and we talk about equilibrium dynamics. Lambda is the diagonal, is the spectrum of the matrix of the eigenvalues of A. O is an orthogonal, random orthogonal matrix. It's okay because I have my observable. I suppose that I diagonalize it, but it's an A, but in another base. It's in the basis of the eigenvector of the Hamiltonian. Okay, I don't want to look at it in the basis where it is diagonal. Yes. Yes, if you want, if you remember my other lecture, OI alpha or my C alpha. So these are the eigenvector component of the eigenvector alpha in the basis of the if the eigenvector of A. Lambda is fixed and I diagonal. So if you want, maybe I write it down. Okay. Okay. Oh, should have written. Maybe I write it here. So A in general, I can write it diagonally. So in its diagonal form. Okay, you know it's trivial to diagonalize an operator usually. And then I want to look at A alpha beta, which is sum over I, E alpha I E beta. But this is nothing but that okay, so now I do I told you that it's going to be a little bit technical and I need some notion of random matrix theory. Random matrix theory. I'm interested, first of all, in the large n limit of matrices. This is good because we are going to do statistical mechanics, so our matrices are actually huge. And in this limit, we expect self-averaging behavior. which means that if I look at moments, or in particular also at the spectrum, the mean distribution of eigenvalue, this is going to be a self-averaging properties, which means that if I take a random matrix, it's or actually that if I take the average overall the ensemble of my random matrices, it accurately represents the properties of one single sample. And the type of ensemble that I have in mind are so-called rotationally invariant. Are so-called rotationally invariant ensembles, which are usually modeled. The probability of the matrix element of this ensemble are also called the matrix model. It usually is a generalization of the GOE, if you want, where the probability of your matrix element is determined by the exponential of the trace of some potential of the matrix. So V can be a polynomial, for instance. And here is the measure. And the nice property of this type of ensemble is that it's rotational invariance, which means that it doesn't. Yeah. Yeah, for the moments, for the quantity that you look at, yeah, average are not self. Yeah, for what I want to say. Yeah, you should, yes. Yes, I want to say that for what I mean, there is some, what I need, there is some self-progeny. And the nice properties of this, so the rotational invariant, because P of A, so the probability of observing a matrix is completely independent on the basis that you are looking at. So, so the functional form doesn't change when you change the basis. And also the Lebesgue measure is invariant under this change of basis. And the other time I use, we are talking about GOE, which is the extreme case where this D is a square. But in that case, I was thinking to the GOE as a model for the Hamiltonian, and I was interested in the eigenvector, and the eigenvector are completely random. In this case today, I'm thinking to this type of probability distribution as a model for my matrix elements, not because I'm thinking to eigenvector, I'm thinking to the matrix elements. And if you see this object here, I'm saying that I want to look at my matrix element in a random basis. So if I want to talk about properties of this matrix, I'm going to average completely uniform over all the random orthogonal transformation. And in the similar way, in this type of ensemble, if you want to talk about properties of the matrix element, you're going to average uniform over all the basis, because in the end, it's completely, all the properties are completely independent on all. And a quantity which characterize the ensemble is the eigenvalue distribution, which is basically the histogram of your eigenvalues. Which this we are talking about self-averaging as this self-averaging. And okay, and now I need to introduce for you just two random matrix transform. One is the which is I call it G of Z. And it is the average, but also here the average is not really. of the trace of the resolvent. And this means that you can write it so this is called the Stieltjes transform of the density of eigenvalues. And the nice properties of this Stieltjes transform is that it is a sort of generating function for the moments, because you can develop in power series this factor here, and you can write that g of z is equal to 1 over z 1 plus sum over I from 1 to with mi is the moment, which is the normalized trace of the power of A. Okay, so this is the Stieltjes that probably you have encountered, and there is another transform which allows me finally to define what are the cumulants, and this is the so-called R transform. It is defined by taking the inverse of the Stieltjes and okay, you subtract this term here, but take the inverse of the Stieltjes, and it's a bit cryptic, but mathematicians or physicists, I don't know, I've noticed that you can write this in terms of a power series around the origin, where this Taylor expansion around the origin that produce some coefficients, and these coefficients are my beloved free. Why you should be interested in? So this is will be just an appetizer of free probability, which I think I cannot go into detail today, but at least you can already start to define things, and if you use this definition, you can express free cumulants in terms of the moment, and you see that you can write them as in terms of the moment. I already told you the other time that up to order 3, I wrote the expression just to have it. And what is important is up to order 4, because it is the point where free cumulants start to be different from the cumulants that are usually used in for random variables. And I give you just the expression, it's not saying much, but so it is not saying much, but why should be interested in free cumulant in a first approximation is that for a GOE, you know that the rho, the density of eigenvalue is the semicircle. You can compute the Stieltjes. Now I don't remember what is its form. And then you can compute the R transform. And the R transform is simple, which means that in this the power series stops at the first order in omega, but which is the second free cumulant. Ah, yes, yeah. Yes, I wrote it in my notes. Which tells you that all, for a GOE, all free cumulants larger than 2 are equal to 0 in the end in probability. run for random variables. So often, what is accumulant saying? It is saying the difference between what is Gaussian from what is not Gaussian. And similar here in a random matrix, this free cumulant is saying the difference between what is a GOE and what is not. So Z is this, sorry, call it G. Is the still just. Okay, so I need to define what is this generating function of free cumulants. And now I will go into a proof of the formula for the free cumulants I was telling you. So what I'm going to use is the low rank Harishandra. This is on Zuber integral. And so this integral is a famous one in the physics, mathematical physics literature. So it is defined as the integral over the R measure of the group, which could be the orthogonal or the unitary group of space of A omega. So G, as I said, can be the orthogonal group or the unitary group. And A and B are two n by n symmetric if you are working the orthogonal group or Hermitian matrices. And so this integral has found several applications in physics, ranging from disorder system to quantum gravity, of which I know. And if G of n is unitary, there are exact results for all the n. The problem was that these results, they involve a determinant. So they are, even if you can write down the expression to get the asymptotics is difficult. However, there is a nice result. What is that? You can have some more understanding of the problem, which is the case when the matrix A has a low rank. This case, so you assume that the eigenvalues of A are lambda 1, lambda p different from 0, with p much smaller than n. So, and all the other one are zeros. And in this case, so the result, so you can prove it quite easy, is that EFB is equal to the exponential of n over 2, the sum over I from 1 to p of V of WI. W is W fix is the primitive of the R transform, and this you understand now why I want to introduce it. And in the, as I told you that you can write it in a power series, you can do this in terms of the free cumulant in this way, V of x. Now, if you say this, if you represent it in this power series, you can also think to the sum over I and I as the sum over all the index n of the free cumulants times the trace of A to the n divided by n. Okay. Okay, and this is the results that I need. And then I'll show you how you can use this low rank Arishan-Ricks-Zuber integral in order to prove the correlation between matrix elements. Yes. Yeah, sorry, you good point. So when I was saying for the U, you have that result, it's valid at any n. This is a large n result. And it is valid both for the orthogonal group and for the unitary group. Sorry? Beta. Ah, no, sorry, no, you're right. So, the matrix B, I can explain why. So this is their transform of some spectrum, and this is their transform associated to B. It's okay? You know, because if you have three cumulants, you can think you can express in terms of the moments, and so are the moments of the free cumulants associated to the spectrum of B. Sorry? Yes, is yes, you was a bit, I don't want to use too much notation, but the precumulants are associated to a distribution of eigenvalues. Sorry? N over 2, yes, what? No, I think that if you define it like this with a positive sign there, you get a positive. But yes. Yeah, the cumulant are of B. So the eigenvalues of lambda are encoded here. I'm summing overview of lambda I. The view is this. So if you want, here there is the trace of A. A is here and B is here. Sorry? Lambda are here because the trace of A to the n is a sum over lambda I to the n. Yes? Depends on B, sorry, I didn't, it depends on B. Yeah, this is a nice formula that I think is not so much well known, but it's very useful in the end. So, and now I come to this toy TH. I already told you that I have my operator that I look in the basis of a random basis. So it is defined by its spectrum and this random orthogonal transformation. And I want to prove this formula. Okay, this means, so let me call this object L of P. Ah, sorry, I should tell you who has derived this result. I don't know. So this result, I'm not going to write it down, but this formula was present in a paper by Marinari, Parisi, and Ritord in the 90s. It is formalized by mathematician Alice Guionet and Maida in 2005. And actually, I learned it from a review of Boone, Bouchot, and Potter in an appendix, but it's quite clear in 2017. So I want to prove this, and then I write this average. So I'm averaging here over this orthogonal transformation or orthogonal matrices. And this, therefore, I write this as the average over of O lambda OT to the alpha 1, alpha 2, O lambda OT, alpha 2, alpha 3, O lambda OT, alpha P, alpha 1. But this object here can be written down as 1 over n, the product of L, which goes from 1 to P, of the derivative of B of L. I will tell you what is B, of this low rank Arishandra Zuber integral. So what is M of B? So you see it is a sort of generating function. So this M of B is a matrix of low rank. First of all, let me say that as the result, the problem is permutational invariant with respect to the indices. I call this alpha 1, alpha P. I call it 1 P. It doesn't change anything. And this matrix P is a matrix of size n because it has to match, but it has a block of size P. And then the other one are 0. And this block of size P is this cyclic B. Sorry, on the diagonal there are 0. And it has B1, B2, BP minus 1. And then here 0, and here there is BP. B1, B2. That's the cyclic form. And if you use that here, you see that when you take derivative, and this should be evaluated B equal to 0. You may come down this element of this matrix here, which form this cyclic structure. Okay. Yes. Yes, in the end it will be the same, because this matrix M of B, you see that it is 0 apart from a block of size of P, and it is the rank of this matrix. So now you see that the object I wanted to compute is expressed in terms of this integral, but I already told you the results, so I don't go actually in all the detail. You can, yes. Oh, sorry, what? So I want to pick up 1, 2, 2, 3, 3, 4, 4. So I'm saying that instead of taking this alpha all array spread in the matrix, it doesn't depend on the order. So I can rearrange my index as I want and just fix them to be 1 from 1 to p. And so my matrix in the end is just the first block that simplifies. Because in the end, I want to arrive to that result, which is independent on the indices. So if instead of computing 23, 54, I would have computed 1, 2, 3, and 4, would give the same result. Yes, lambda is deterministic in this case. Yes, it's fixed. It would be the same because in the end you have this self-averaging province. If you want, it is yes, you can average over a eigenvalues. It will be the same result. You have to be careful with the average over eigenvalue when you look at rare events, but in this case, it's the same if you average over. Yeah, I will write it in. So a better way to see if you want to put it into contact with ETH is to, instead of replacing that term, which is n to the p minus 1 to a sum over different indices normalized by n. It's the same as it doesn't depend on the indices. You can sum over the indices or say that they are n to the p minus 1. But the best way is to think that they are summed. If you want to make it at the end, we want to put connection with ETH where you don't have this permutation invariance, and it's better to sum over the indices. Sorry, I'm saying. Yeah, because above I'm averaging over the basis, the eigenvectors, if you want, of H, which is equivalent to averaging over O, the orthogonal transformation. It's flat. It's the R measure over the orthogonal group is flat. I don't know how to write it down. It's not possible to write it down for large. It is encoded in this D of O that it's okay. So I don't go in detail because it becomes boring, but you then that using the formula, you get that L of P is 1 to the N, deduct from L1 to the P, B to the B to the P of the formula that I was writing before. And okay, just a little bit of exercise, and you see that, but you see that here there are the two cumulants, and so kappa n and this kappa p. Yeah. And you can find these results. I'm sure that coming from the quantum community, you don't find it never. It's in a paper by Antoine Maillard and a bunch of people, including myself, which is about machine learning. Okay, what time is it? Sorry. Is already? I have half an hour. Okay, good. Okay, with this, so I wanted to tell you this. I don't know. I like it. that is a bit much. But to this, we want to do something for the quantum systems. And so we study, now we pass to the chapter, which is the dynamics at equilibrium. Sorry? No. Actually, at the end of my lecture, I will just for the ETH, we use also other type of assumption, and it's very powerful to, you can think that you can use it by changing the matrix B. You can generate many type of diagrams, not only this loops with different indices. You can generate other type of diagrams, and it's easy to get a scaling of them. Okay, so we have our many body problem, and you want to see the dynamics of a two-point function. This is, of course, in thermal equilibrium described by a density matrix. And so this term here, I always use the spirit of ETH, which is to look at it in the write it in the basis of energy, and it is given by two different terms. Which is a diagonal part, which is time independent, and an off-diagonal part, which contains the information about the time. And so call this one, and I call this two. And then now I want to use what is encoded in ETH to estimate this integral. So when I do this, I also indicate that I have a sort of self-averaging, because I want to estimate to compute my correlation function in terms of ETH, but by averaging over the ensemble. So I expect that my system, which is precisely determined in some sense, is well described by an average over this fictitious ensemble. And the term 1 is equal to 1 over, okay, I already told you what it is now. And the standard curve of ETH is always to in this large n limit, where you replace alpha as the sum over, as an integral over the energy of your density of states, and this is a density of state is exponentially large. And doing this, you end up in writing this integral as an integral over b e to the e, the Boltzmann factor. And now I plug in the ETH ansatz. For the diagonal matrix element, I don't care of their fluctuation, which are encoded in those random numbers. I'm just interested in the leading contribution, which is deterministic quantities and a function of the energy. And so this I should do this. And also doing from here to here. No, actually doing from here to here, I'm not doing any averaging. I'm just saying that this is big with respect to the fluctuation, which is the idea of self-averaging. And I do, this is extensive, and this is also the energy scale extensively. And so if I I could write this in terms of the energy density and do a saddle point with respect to the energy. This is what typically happens in statistical mechanics, but now my observable is also a function of the energy. And what happens is that this is going to be the saddle point simplified with basically the partition function, and you just have the square of your matrix element evaluated at the energy associated to the temperature beta. This is exactly the same result that you would have obtained if you would have computed the average of A at temperature beta and del squared. So there is an equivalence of ensemble in this encoded in ETH. And yeah, not the weakling sign, just meaning that this is as a fluctuation on top of this, there are fluctuations. So either you say that you know, in the ETH, you have the diagonal part plus fluctuation also of the diagonal. And now I come to the dynamics, which is the second one. I do the similar tricks, but now in 2 I have a double sum, so I'm going to pick up a double density of states, which will be compensated by the fact that the diagonal matrix elements are extremely small. So overall, the end result will be of 1, which is what we expect to be. So I write the double sum in this way. Then have the Boltzmann factor. I have the phase of the dynamics, and then I plug in the ETH ansatz. So actually this is omega. So where A plus, I remember that is A alpha plus A beta divided by 2, and omega is A alpha minus A beta. And okay, now I have to make a change of variable because ETH is naturally written in the variable, in the symmetric and antisymmetric variable. Instead, when I do the sum, I have to separate the energies. And so doing this change of variable, I need to, so in those density of states, you have an entropy which depends on E1 and an entropy which depends on E2. And I need to expand then around the mean energy, which is E plus. Ah, yeah, sorry. Yeah. It's okay. Let's say it. No, I cannot call beta in another way. How can I call it? 1 over T. No, this is 1 over T. Ah, E beta. Ah, sorry, E beta. No, I was thinking to the Boltzmann factor. Yes, E beta is the, 1 over T. It's the energy associated to T. And so, and with this, so you need to expand S E1 slash E2 around. I want to make this change of variable, which is E plus. But then you get minus or plus ds plus times omega over 2 plus 1 over 2 ds square over d square, evaluated again. And so in that expression, you have the exponential of S1 plus S2 So this means that you have S1 plus S2, E2, S of E2 is equal to twice S E plus. This is minus, this is plus, it cancel. And this is actually negligible if you want, because the entropy is extensive, but the energy as well. So you take it twice the derivative. This is going to zero. This goes to zero in the large size limit. And so this means that if you plug all together the things in the second expression, so you have that one of these S simplifies with the S coming from the diagonal matrix elements. The other one will contribute to pick up in a similar way as the diagonal part has done a particular energy and simplifies with the partition function. And just let me go to the point, which is that the average over 2 is equal to the integral of omega of E minus beta omega over 2 e to the I omega t f of E of beta 1 over t omega squared. And so this is the final result for two function. You have seen that you can, first of all, let me make a comment. You see that this function f of omega, so here there is an exponential of minus beta omega 2, but this integral of frequency is going basically from minus infinity to infinity, which means that this becomes huge when you go to negative frequency. On the other hand, f of omega is symmetric, because the matrix elements are A alpha beta is equal to A beta alpha, at least in the symmetric case. And this implies bound for this function f of omega, which means that f of omega has to be smaller than E to the minus beta omega over 4. Which means that if you look at your matrix, and if you are interested in ETH, I suggest you to look at it once. Really, you would see that your matrix, your operator in the basis of the energy will have. So I don't know how to. You should see a picture, but this is the matrix. So and this means that it goes the energy. This value here encodes the dependence when you move along the diagonal, but the frequency encodes the dependence when you move away from the diagonal. And as you see, it decays extremely fast when you move away from the diagonal. This means that it's very far from being a full random matrix. It's something which has a well-defined structure. And okay, let me make some comments about this two-point function. The first is that if you look to the now it's not there anymore, but if you look in your notes to the expression of the two-point function, it's just basically the sum over alpha beta of A alpha beta squared. So it's basically the sum of the variance of the diagonal matrix element. So there is no, you don't care at all about correlation between matrix element when you look at two-point function. Depends only on the variance of A alpha beta. And if you look at this formula, you see the variance of this matrix element is nothing but, apart from this Boltzmann factor here, is nothing but the f of omega is the Fourier transform of the two-point function. And therefore you immediately start to realize that in the many-body problem there should be some more information apart from the two-point function. There must be something else to be as general as possible to describe the quantum many-body system. So I will say here more information is needed. And you immediately see that the situation is different indeed if you go to high order correlation functions. Because you see that in order to understand multi-point function, you really need to say something about that correlation. Because if you take A of T1, A of T2, A of 0, this will be the sum over alpha 1, alpha, let's say that you have P of them, alpha P, the Boltzmann factor. Here there are the phases, A of T1, A alpha 1 minus A alpha 2, blah, blah, blah. But in the end, what is important that I want to stress is that you have these cycles. So you have, you need to characterize this correlation. So in the 2-point function, you have just the square of one matrix element. Here you have different matrix elements, and you need to know how they are correlated. And this cycle structure resembles a lot. So let me say that what we no, first of all, let me say why we arrived to this point, because if you are here for quantum chaos, and you probably know about the quantum Villard exponent, and we wanted to understand with DTH the out of time order correlator, which is a 4-point function. But okay, we had to go beyond that because there was only the 2-point function in the DTH ansatz. And with this, so I already told you that my inspiration was coming from random matrix theory. And so you can guess how we try to say what other information should you assume that is present in this matrix element ensemble, which, by the way, as I said the other day, maybe Julian will talk about the ensemble. Okay. Okay. So I'm not, it's very difficult to write this ensemble. This is what people are trying to do. And just let's say that you have to, I wrote it here, it is a ETH that we started to work on this before the function. The paper is 2019. And so what just so the first assumption here everything is an assumption, but the first assumption that we make, you have in the same spirit as the toy ETH, you have this cyclic products of different indices. So, and this, we say that the scale, no, P minus 1, so E. So, E here is similar to what it is in ETH, is the average energy. And no, not alpha P, alpha E. And omega E are the frequency. And what I call here R2 is the square of f of omega, which characterize the size of the diagonal matrix element in ETH. And this term here, bizarre term, it says that these correlations are extremely small, but is the analogous of the term 1 over n to the p minus 1 that you have seen in the matrix model. And so it says that these correlations are extremely small. This matrix element, they look like if were almost uncorrelated. But at the same time, when you compute, you use this term to compute correlation function, you sum over many indices, and each sum will carry a density of state, which compensate exactly with this with entropic factor here. And so they are not so small in the end. And the second assumption that we make, you can prove, I don't know if prove is the exact word, but you can rationalize it. In the random matrix theorem, and we have proved it in that paper I was talking about for the average of recumulants using the low rank it's on Zuber integral. And here we assume that is true also for our many body problem. And it is that if you want to compute a moment, you see there that you have these indices. They have to form a cycle in the sense that you go from alpha 1, you travel along all these indices, and then you go back to alpha 1. And maybe there are some repetitions. I was telling you that this should definitely care. And for me, this is the building block of all the correlation, where all the indices don't repeat. But you have other diagrams of this term here where the indices repeats. And well, what I claim is that only cactus diagrams survive. What is a cactus diagram? It is in this representation. Here, it is a diagram where it looks like really a cactus. So no, let me first say it. If you have a 4-point function, you have this, and then you would have also a term like this. Is a 4-point function because you have 4 edges, so 4 matrix elements. This is a cactus. It means that you see that it is made of loops, but it's a tree in the sense that there are no loops of loops. So if you join each loop just in one point, and you can cut it. What doesn't contribute to a 4-point function in random matrix theory, but we say that it doesn't contribute also for a term like this. This is not a cactus. So if you want a cactus of higher order, is just something where you make many boards, many loops. I don't know what is. Maybe. What are the binary correlations? Yeah. This as a, if you are normalized by a factor n to the p minus, or better, sum over all the indices, this is not 0, which means that these are not 2-point correlation. This is higher order correlation. Now let me finish the one of the cactus. So I want to say that you have many diagrams, and in particular you have the simple loop. The simple loop is a type of cactus. Just it is a trivial one because you have only one loop. This is a type of another cactus. And what you can show in using this low rank Zuber formula, and this on average, you can cut it here, and it is equal to the two, the product of two. And so what have different indices. So this will be a K2, and this will be a K2. So this character, this is KP, this is K4, and this is the product, is K2 squared. And so, but this again suggests that you have many diagrams, but on the other hand, what they matter are these cacti, that's right. But they split into simple diagrams, and so and you neglect what is not cacti. And so this is the second assumption that we make. This seems I don't know. The point is that you have too few indices. So when you have many indices, you gain because you introduce a density of states for any sum over indices. This has a lot of edges, so they are very small, but not compensated by summing over indices. So I explain. Okay, so basically the bottom line is that these loops are the building blocks. And we can put in, okay, this is another chapter. We can put it into connection with free probability, that a branch of mathematics. No, I don't know, but it's a branch of mathematics who studies non-commuting random objects. Thank you. Question? The low rank. The low rank. So if you have a rank 1, it's very easy because well, I don't know if I'm able to do it on the spot, but so if you have a rank 1, you have your matrix is basically a vector, is defined by a vector, is VI. So what you mean is that you have E, so it is trace of a projector, if you want, is rank 1, and then you have O lambda OT, and this now let's write it in some basis. You have some basis I, J, I and J. And you put J and I. And the measure of this is simple because it is just a random vector. So basically it is just the delta of sum over I, see this overlap here, I square. This is the measure. This you can write delta function, exponentiate it with Fourier transform, do a saddle point. It's not complicated. Sorry? Yeah, this is a type of phi. This is when A is rank 1, you can write it in this way, right? Or not? Yeah, I think so. Yes, it's a projector. So maybe with some, yes, there is a with some lambda, which is quantified. Taken by the B is here. Yes, I don't know the current status of the thing. Maybe square root of n. I don't. For sure, if it is order one, is good. Yeah. Yes, tell me. So,